Hello everybody, and I'm Lee Mallet, writer, urbanist and regeneration consultant, and your host for this evening. Welcome to a rather special edition of engineer Eckersley O'Callaghan's popular webinar series. I'm told we have more than 400 people registered for this webinar. It's a special edition because HAL architects and engineers Eckersley O'Callaghan will be describing how the sky pool at Embassy Gardens in Battersea, developed by Eco World Ballymore, was conceived, designed, created and commissioned. It's a remarkable feat of design and engineering, with many creative technical people involved, not least manufacturers Reynolds Polymer Technology of Grand Junction, Colorado, who specialize in doing amazing things with acrylic. Now, as you can see, we're using the Livestorm platform, and on the right hand side of your screen you'll see the chat and questions functions. Please say hello and where you're joining us from on the chat function, and please ask any questions via the question function. The webinar will focus on the design and engineering of Skypool, and there will be time to answer some of your submitted questions after we've heard from Eckersley O'Callaghan and HAL. We're going to hear first from architect Hal Curry, founder of HAL Architects, and then from Brian Eckersley, founding director of Engineers Eckersley O'Callaghan. Also Sam Gregson, senior structural engineer and digital design specialist. And finally from Graham Colt, Eckersley O'Callaghan's technical director, which should take us up to around about 5 o'clock-ish. I won't blind you with statistics or engineering science, as I'm sure EOC will do their best. But in Skypool, London has a new landmark, just in time for whatever the next phase of the pandemic holds for us all. Its key characteristic is perhaps the clarity of Skypool itself, designed to enhance that ancient relationship between humans, water and landscape, a fundamental theme in everything that architecture, engineering has tried to achieve within modernism. Sci-fi films that seek to predict the future remain packed with that enduring aspiration as our world accelerates into a fourth industrial revolution. So let's go to our first presentation by Hal Curry of HAL Architects. But before we do, during presentations, please mute your mics and turn off your cameras. Over to you, Hal.
Thank you, Lee. Oh, great, got the slides. Yeah, thanks, Lee. And following on from your introduction, I'm going to provide some context, both in terms of the pool setting and also how the idea came about, the idea of Skypool, and how it also evolved. So this is the team, I'm sure you're familiar with, and we'll crack on. So just sort of setting it in context, and you've got on the left-hand side of the slide, Battersea Bridge. We can't quite see Vauxhall Bridge to the right-hand side of the slide, but obviously there's this huge new area of development between these two bridges, just to the south of the Thames. And you can see in the red line is Ballymore's landholding, which is all around the new US Embassy. Now this was a few years ago what I refer to as shed territory, DHL, post office sorting, new Covent Garden Market, and the odd car dealership. So it was very much that type of environment, and also very much, and still has the challenge of Nine Elms Way, a very busy thoroughfare running sort of not parallel to the Thames, but it really is a key route running east-ish, west-ish. So there's also, it's a critical sort of part of the delivery and involves all the developers and landowners sort of managing to communicate and talk to each other, is this idea of, which is picked up in the Farrell Master Plan, of a linear park, again linking Vauxhall Bridge to Battersea Bridge. The sort of, in terms of the diagram, the blue dots are the Thames, the black dots to the base, the railway line, the Waterloo railway line. And this idea of the park pulling people off the busy 9 arms way, so pedestrians and cyclists using that link. We've been involved in Embassy Gardens for over a decade in various guises. The original massing density and configuration was set out by the Farrell's master plan. And then we worked alongside Farrell's and the other detailed design architects during the first phase, which set and sort of tested some of those parameters as well, so as sort of shown in that bottom middle slide, where we all sort of bring our own models to the fore. We're working alongside fellow architects HMM and FCB on the first phase of the residential build, which was completed in 2012 for Ballymore, with the shared ownership building alongside for Peabody. These are essentially simple residential buildings which belie the density of the scheme and are rooted in its interaction with its location. Brick buildings to ground, around raised courtyards, a southern facade with extensive views out over London, generous balconies over the new linear park. So this gives you a sort of plan and overview of Embassy Gardens with the completed first phase to the left-hand side, phase 1 to the left-hand side of the Embassy. And then with the phase 2, where Skypool's located to the south-ish of the Embassy, the grey blocks. So you've got 3 buildings, interconnected buildings, just to the south of the linear park, and then a PLP building, AO2, to the northeast, and a new consented plot to the very northeast of Nine Elms Way. And there's also a consent for a new hotel building to the west of the Embassy. This diagram is sort of a 3-dimensional version of what you've just seen, with obviously the US Embassy at the centre, and the residential with some commercial buildings forming, I suppose, a necklace to the Embassy. Each plot having a strong perimeter, heights ranging between about 10 and 23 stories, some restrictions in terms of height, in terms of the viewing corridor and silhouette, particularly to the Palace of Westminster when viewed from bridges to the east. This doesn't show the development to the east of the RNF site, which is currently underway, which has buildings of much more significant scale, up to 60 stories in height. So when Ecoworld Ballymore asked us to help develop the next phase of Embassy Gardens, which is about 900 apartments across the 3 buildings, we looked carefully at how it was integrated with the overall estate, and building on the architectural language of phase 1. Someone's referred to it as a scheme of bricks, balconies, and bridges, and Skypool sits within the sort of balcony, certainly within the bridge element of that. And also, as part of the client's brief, I'm sure we'll talk about this more, we were asked to provide a high level of amenity, such as pools, gyms, cinemas, working from home areas, and so forth, which was new to us in terms of an offer more akin to a sort of high-level hotel than a residential offer in our experience, and presented some new and interesting challenges. And as part of the phase 2 offer, we were asked to look at creating a 25-metre pool at level 10. So we're now going to talk about how the sort of idea evolved. So we've got buildings to the left and the right, the pool shown to the right-hand side, the 2 roof areas with the gap between. So obviously, if we placed it to the east, it wasn't going to fit. If we placed it to the west, it could just about fit, but there were concerns about the adjacencies of plant and not having enough room to breathe. So that sort of led us on to thinking about the bridging structure in terms of placing the pool between the 2 buildings. The idea of a sort of high-level swimmable bridge was born, and this obviously also had the advantage of providing direct access to the pool from both left and right. The idea of a bridging structure holding water or an aqueduct was discussed at early meetings, and while we knew it was doable, we knew there were significant complexities in terms of linking the 2 separate buildings. And I know Graham in particular or Sam will look at this later in terms of the settlement between the 2 buildings, one building being built before the other, and the difficulties in terms of the movement between the 2. And also, obviously, challenges in terms of, as usual, in terms of the cost plan, and we didn't really account for this pool in terms of the original thinking and scope. The initial conversations were really centred more about an enclosed aqueduct filled with water for residents to swim across. The idea that this would also create a framed entrance between the two buildings into the central courtyard from the American Embassy side and to provide a striking landmark to waymark the entrance. We then started to think about the idea, then having the idea of the swimmable bridge, we then began to think about views in and out and the potential for taking advantage of both views across Embassy Gardens, but also to the north in particular, across to Chelsea and into the West End. And we sort of, the discussion evolved in terms of providing windows to the structure to allow swimmers to see out and passers-by to see in. When we were discussing this with the client, in particular with Sean Marine, the chairman of Ballymore, and Peter McCall, who's the head of construction, the message was sort of unequivocal, really. So if we're going to do this, Sean said, then let's do it properly. It needs to be transparent. And I remember leaving that meeting thinking, well, that's not going to work. And while transparency was a brilliant aspiration, it was also a real headache. We evolved initially a steel and glass hybrid, but the complexity in terms of detailing soon became starkly apparent. And we'd end up with, and again, I think Graham will pick this up in particular later, we'd end up with so many stainless steel fixings, the lamination, which would lead to further refraction through the glass, that the big idea, this brilliantly transparent vessel shimmering between two buildings, would be entirely lost. Oh, I've got some technical. Event is full. Can anybody else see that? Ailish, can you deal with that?
Yeah, Hal, you could just close that window.
So, rather than the technology, but we didn't let the technical complexities lead us off track, and we started to develop the scheme for the pool based on achieving as transparent a section as possible between the two buildings. This idea of a stainless steel tub at either end, which we embedded within the buildings to the east and west. The tubs, which again, Eckersley Callahan will cover in more detail, really contain what we refer to as the gubbins. So in terms of the filtration systems, the lighting, the pool cover, access steps and so forth, which allowed us then to keep the central section as clear and transparent as possible. The three elements, clear central section and the stainless steel tubs to either end are sort of shown on the cover of the Skypool brochure, which we developed during the sort of early stages in terms of helping us and others to better understand the process. And again, the process will be further picked up later on by Eckersley Callahan. In the meantime, a work in progress CGI found its way into the Evening Standard property section and attracted an extraordinary amount of interest. So while the concept was simple, it was clear that its implementation was anything but. And I think it's fair to say that at this stage of the project, none of us were entirely sure that the image could be delivered, which is where Brian picks up the story.
Thanks very much, Hal. Can you hear me? Give me a nod or a thumb. Yeah, thanks, Graham. Yeah, I am Brian Eckersley, one of the founding directors of Eckersley O'Callaghan. So these were essentially the images that we were presented with, how to build something like this. And the reason that Hal and Ballymore came to us, well, here we are actually, we have the plan which shows the transparent structure spanning 15 meters between two buildings. As you can see, there's 5 meters of pool sitting on the building at each end, and this 15-meter span in between of transparent structure. And it also, as you can see, it doesn't span perpendicular to the two buildings. It spans at a skew angle, so that also introduces some additional engineering and analytical complexity. And here we have it in section. So in total, the pool is 25 meters long, 15 meters clear spanning in the middle. It carries 1,200 deep of water. And there is this stainless steel tub at each end, which Hal described earlier, which forms the overall 25-meter length. And it's 35 meters up in the air, 10 stories. So in total, that is a weight of 150 tons of water. And as all good Londoners know, that is the equivalent of approximately 15 double-decker buses. So in terms of material choice and what I was about to say before, the reason that Hal and Ballymore came to us, we have over 20 years and more developed a specialism in transparent structures, particularly in glass, in our office at Eckersley O'Callaghan. A lot of this work has been done for Apple. So here, for instance, at Fifth Avenue in New York, the Apple store there, which has become one of the iconic structures on Fifth Avenue. This is a 10-meter cube, which is an entrance to the store underground, constructed entirely from structural glass in a very minimal fashion. And then much more recently, this is the Steve Jobs Theatre on the Apple campus in Cupertino in California. This is essentially the entrance to the underground theatre where Apple launch all their products every year. So this is a 50-meter diameter roof of carbon fibre weighing approximately 100 tons, and it's supported entirely on this wall of glass, which is about 7 meters high. So this is the world's largest glass-supported structure. And we've also done some pretty spectacular staircases for Apple, which have to carry significant live loads of people on them, but never as high as the opening night, one of which you can see here. And along the way, we've worked with the best fabricators in the world, helping them to develop the techniques to fabricate ever larger panels of glass. So here we have what were at the time the world's largest laminated curved toughened glass panels, which were made for this project at IFC Pudong in China. But in many ways, the seed for all of those projects came from this much more modest thing, which is something that I worked on as project engineer almost as soon as I graduated back in around 1990, which was a glass extension to a private house in Hampstead with Rick Mather Architects. And I was working for the engineer Tim McFarlane, who was one of the pioneers of structural glass over in that period. So here we had what was pretty much the world's first laminated glass load-bearing frame. We had glass beams spanning about 3.5 meters, and we had the short glass columns, which were about, 1,500 millimeters high. So it demonstrated that glass could be used to carry significant loads in this structural way at that time. And then shortly after that, I also worked on this project, which again was a private house in North London, which was a swimming pool. It was on the third floor up of a building. It had this glass bottom, which was a series of glass panels, each supported on 4 edges, 2 of the edges of which were glass beams. But of course, glass needs to be jointed, and sometimes using fairly complex bolted connections. And for the engineer, that's where we have the most trouble in proving that glass structures will work. And these have to carry significant loads and ensure the safety of the occupants of any glass structure. So for Skypool, our first instinct was that glass would be the appropriate material to make this structure work. So we did develop an early solution using glass, and it was something like this. This simplifies it rather, but essentially there were these 2 big glass beams which formed the side walls of the pool. They picked up secondary glass beams spanning in the short direction, and those in turn supported glass panels along the bottom. And then in order to to prevent the water pressure from pushing the big glass beams outwards on the side, we then had these horizontal glass shelves which would restrain that load. But as you go through that solution, the loads at the end of each of those beams all need bolted connections. The stresses around those connections add to the stresses in the panels due to them acting as beams and carrying the load in the other direction, as well as the hydrostatic loads. You then get increasing stress concentrations around the holes, so the bolts need to get bigger and bigger to deal with those stress concentrations. And then here is one of our other staircase projects where we have the balustrades of the stair, which are acting as glass beams, spanning about 12.5 meters in this case. And you can see the connections that you need just to carry glass treads, which become, not visually insignificant in the overall effect on the structure. And then, as well as that, even in carrying these loads here, we have 5 pieces of glass laminated together to make a safe beam in this situation. And as you add pieces of glass together, it gets more and more green, it gets less and less transparent. Now, the solution Skypool wouldn't have needed as many pieces of glass laminated together as this, but you can see the visual effect. Transparency is reduced, the bolts further reduce transparency, the structure gets heavier and heavier. That means that you need more structure in it to carry those loads, so you end up chasing your tail. It didn't really seem like the right solution. So it was actually Graham Colt, our technical director, who will speak shortly, who suggested that perhaps we might look at acrylic as the appropriate material to use. Now, acrylic is used in almost all aquaria, and it's used in situations where it carries pretty significant loads. So, we have the walls of aquaria, which sometimes might be 10 meters high. So there's significant hydrostatic pressure on them. And there's also the project in the middle at the top there, which is in a hotel in Berlin, where there is a lift which goes up the middle of that acrylic tube, which is also an aquarium. So I think that goes up 5 stories. So again, there are significant loads there. And Reynolds Polymer Technology in Grand Junction, Colorado. They are the world's premier specialists in creating acrylic structures. And they've done a number of these projects that you can see on the screen in front of you. So, and we'd worked with them also on a number of projects in the past on much smaller scale structures. So we went to them to see if we could figure out a solution on how to get this built. And in very simple terms, this is what that solution was. So we have this U-shaped acrylic structure, which is spanning 50 meters, skewed, as we said. It has those stainless steel tubs at the end. The whole lot is pulled together with tension rods, which enables everything to move together, sitting on top of these buildings. And you also get this seamless construction, other than the connections with the stainless steel, so it ensures the watertightness. So if we look very briefly at the properties of acrylic versus heat strengthened glass, acrylic is more transparent, as we said. There's less visual distortion with water because its refractive index is more similar to water, which is why it's used in aquaria, whereas glass, you get an awful lot of distortion when you look between air, glass, and water. As a material, it's plastic, so it is much less brittle than glass. It has better impact resistance. It's also less than half the density, so the structure's lighter. The joints are much less visible. They're chemically bonded rather than using silicon and steel. So, if you imagine a glass structure with all the silicon joints you'd have needed between those panels, the water tightness would have been a real issue. However, on the negative side, it's much less strong. It has a working strength of about 1/4 of a glass structure, and it's also much less stiff by a factor of over 20, which means that for a given size of acrylic beam, if you put a load on it, on a glass beam and an acrylic beam, the same load, the acrylic beam will move 20 times more. It will deflect 20 times more. So that's a very significant increase in deflection. However, it so happened that, you know, in this structure that we just looked at, we need this wall on the side to stop people falling out of the water. So we have a beam 3 meters tall, effectively, and it turns out that a beam 3 meters tall, approximately 200 millimeters thick, made of acrylic, is just about what you need to span 15 meters across this gap. So that's it in principle. Now, Sam Gregson is our digital design specialist. He was the project engineer that did most of the smart analysis and engineering calculation on the project. So he's going to tell you how we went from that fairly straightforward concept to a finished engineering design, in conjunction with Reynolds, who also had a significant engineering design input through the project as well. Dan, over to you.
Cheers, Brian. So yeah, I'll just touch on a few of the kind of interesting design considerations. So as was mentioned previously, it's 2 elements: the acrylic bridge that spans the 15 meters, and then what we affectionately call the tubs, stainless steel tubs on each end. So I'm going to focus mainly on the acrylic and how that spans in this. So you've got all the kind of typical loading cases that you'd expect. You've got the weight of the structure, you've got the water, the 15 buses weighing down, but also pushing out on the sides of the walls, and then you've also got wind loads. So they're the kind of typical loads that you'd expect. But actually, what was kind of more interesting and challenging were the thermal loads and the building movements. And so I'll kind of speak to those. But taking a step back, firstly, we had to design to acrylic. So unfortunately, there's no British standard, there's no Eurocode or guidebook that tells you exactly how to design an acrylic swimming pool. The closest we could find was this American standard called the Safety Standard for Pressure Vessels for Human Occupancy. And although there was some useful information in there, really it was geared towards these, which you see on the right, which is a submersible or a submarine, where you've got this kind of acrylic bubble. So it wasn't really kind of what we were looking for. So we relied on the expertise of Reynolds Polymer, who constructed it, and their years of experience, and working from first principles on what we knew about the material. So here's a few kind of interesting things about the material. One of the first things to note is this phenomenon of crazing. Crazing being an amalgamation between cracking and glazing. So this is a word borrowed from the ceramics kind of industry, which you see on the right here. And essentially it's kind of micro cracks that you get on the glazing of ceramics. On the left, you'll see a sample of acrylic, and you see these micro cracks. And it kind of manifests itself in this kind of white kind of cloudiness. You might have seen like kind of plastic. If you try and bend it, it kind of goes a little bit foggy, and that's crazing. So what does this mean in terms of design? Well, crazing happens under a number of different scenarios, but one of which is tensile stress. So if it's being kind of stretched, pulled apart, you'll get these little micro cracks forming on the surface. And this happens at a much lower stress than the stress that would break it. So instead of designing to our original 62 megapascal tension stress, we were actually designing to a much lower stress of 5.5 to make sure that this whitening effect doesn't happen. Another really interesting thing about acrylic is thermal expansion of acrylic. So all elements have a degree of all materials have a degree of thermal expansion, and it's basically growing when it's hot and shrinking when it's cold. Here I've got some kind of numbers for comparison's sake. So we've got glass, steel, and acrylic. So steel expands about 1.25 more than glass, and acrylic is 9 times more than glass. You'll see a 9 times more expansion and contraction for a given temperature change compared to glass. So that's significant. That's a lot, and I'll talk to how that kind of manifests itself in the design. And just to be clear, here we've got a piece of acrylic in the middle, and when it's cold, you see it shrinks. When it's hotter temperatures, you'll see it grows. So one of the interesting kind of ways that this manifests itself is we've got hot water, 28 degrees, inside the pool, and on the outside, on a winter's day, maybe the middle of the night, you'll get like -10 degrees Celsius on the outside. So what that means is that on the inside, the acrylic is trying to grow, and on the outside, it's trying to shrink. So you get this kind of weird bowing effect here. And we actually saw this on one of the kind of first weeks of it being built. As per validating our calculations, we saw quite a significant 80 millimeters of the top kind of moving out. So that was kind of one of the interesting things about this pool and the design. And just to compare, this heavy water that we've mentioned earlier, when that weight comes down, you actually see the sides moving inwards, not moving out, but because the bottom is bending, you see this the walls moving in as a reaction to that. And compared to the 80 millimeters, we actually only get 5 millimeters. So you can see that thermal effects from a deflection point of view are a lot more significant than the weight of the water. So another thing is that on a sunny day, you're going to get 65 millimeters, or compared to a winter's day, a summer day, it will be 65 millimeters longer, and this movement has to be accommodated. It's not just the movement of the acrylic due to thermal expansion, but it's actually the building movements that we need to accommodate too. So all buildings move when the wind blows to some extent. So we've got a differential movement of the two buildings there, 85 millimeters. And then we've got potential settlement of one building versus the other, especially as one site was built a lot earlier than the other site is going to kind of may potentially settle quicker than the other one. So how do we deal with all these movements? Well, essentially the same way that you deal with movements of any bridge. It is a bridge. It just happens to be a transparent acrylic swimming pool bridge. But we deal with these issues in a very similar way. So we're using these bridge bearings, which are proprietary kind of products. On the left there, you'll see a pinned bridge bearing in the middle. And this doesn't move, it's fixed, but it's allowed to rotate. All the other ones on the left can move and rotate freely. On the right-hand side, we have a unidirectional sliding bearing, and it's allowed to rotate, and it's fixed in the other direction, but allowed to slide in the one direction. And all the others on the right-hand side allowed to swivel and rotate and move freely. And this allows the buildings to move differentially to each other, allows the acrylic to grow and shrink. And this is really important, because if we trapped it, if we locked everything in, then as buildings moved, as the acrylic wanted to move, you build up all this tension or this kind of strain and lock that strain in. And you want to be able to kind of free it and let it move and breathe as it wants to. That's the way that you deal with these issues. So here we've got buildings moving differentially to each other, up and down on the top there, and you can see how they kind of pivot about these points. And then on the bottom, you can see that as the buildings move towards and away from each other, or the acrylic expands and contracts, you've got the bearings on the right-hand side sliding to allow that movement. So that was one of the real kind of key things about this design. In terms of the settlement of the buildings, we've got hinges essentially at the ends of the acrylic, and that kind of allows that movement to happen at that location there. So one thing that was very clear was that we don't want to kind of bolt into the acrylic, because as Brian alluded to earlier, bolt causes stress concentrations, and that's even worse in acrylic. So whereas you can kind of get away with it because of the strength of glass, you don't want to do that for acrylic. So no bolting, that was out of the question. And we've got this kind of silicon joint to stop the water leaking. But what happens then if the building moves and you've got a bit of pull on the friction in the bearings, or you've got the acrylic trying to shrink away from that side? What happens to that joint? That's really critical, that we make sure that that silicon isn't going to pull apart and we're going to start getting leakage there. So that was another key thing that we had to consider. And the way we dealt with that is by introducing these tendons that were also mentioned earlier. So we've got two tendons running underneath the pool, and they're pre-tensioned to kind of provide this compression at the ends of the pool. And that means that this silicon joint is never going to get pulled apart. So we're keeping that a nice pressure, even pressure on that, and making sure that no leakage is going to happen there. Of course, you can't just tension it. You can't just tension the tendons and put that compression without allowing it to breathe as well. So what we've done, if we zoom in to the springs on the right there, is introduced a spring stack. And so that means that we're allowing that compression to always be there by tensioning the tendons, but we allow the springs to take up the movement of the pool at the same time. So some other things we looked at was the frequencies of both the structure, but also the water sloshing. And what we had to make sure wasn't going to happen is that these frequencies would be kind of very similar, and that there'd be a resonance between these, because what would happen if the water kind of sloshed at the same frequency as the structure's frequency, is that you'd get this kind of build-up and movement. So that was important to make sure that wasn't the case. And here, so my last slide before I pass on to Graham is the panels. So this isn't, although it appears as one magnificent kind of cast element, it's actually built up of a number of panels. We've got 7 panels along the bottom, 2 on the walls on each side, and then 2 corner panels there. And the amazing thing, Reynolds did an amazing job of bonding these together so that you can barely know they're there. If you look very carefully and you know exactly where these bonds are, you can just about make them out. But they did a very good job of making this kind of appear as one seamless element. And now I'll pass you on to Graham, who's our technical director, and he's going to talk us through the construction and testing of the pool.
Hi Sam, can everybody hear me? Oh, great, thanks very much. So yes, thanks Sam. So the construction period, I mean, this is a very exciting time. It's, you know, I guess it's when all architects and engineers look forward to is a sort of realization of the structure. And, you know, for us, this process kept on uncovering little elements that gave us a sort of sneaky peek of what we'd eventually see on site. But just to go back a little bit, Reynolds situated in Grand Junction in Colorado. It's a lovely place, and you can see the mountains in the background. And it can get very hot and very cold during the winter, and that plays an important part during the fabrication, which I'll talk about later. But I think this is really the first step that sort of brought the idea of what the acrylic is really the right material for this. Is that these are the sort of the cast panels for some of the floor slabs, and you can see how clear they are. I mean, it's really very colorless, if you like. And so the next stage, actually, I should say at this point, Reynolds, one of the few companies, I think the only company who are capable of casting these panels as full slabs. And that was very important, as other manufacturers could offer solutions where they used thinner extruded acrylic and bond those together. And what we felt with is that to make sure we're achieving the highest quality, we wanted to minimize any possible defects. And so taking multiple layers and bonding them together risks inclusion of detritus, hair, lint, all those other things that we see all the time with, well, we don't see all the time, but we've learned lessons from working with laminated glass. The second step is really cutting those panels to shape. And so this is a milling head, and with a rotating head that generally grinds and cuts away the material, and all the sort of snow-like material you can see on the top of the panel. That's actually the acrylic. Following that stage, the scores and the marks left by that cutting head are polished out by hand. And for this project and for Reynolds projects, there's a huge amount of hand polishing taking place with highly skilled labor, and that's really down to the fact that there's not a better way of really doing that, and really achieves a high level of quality. I mentioned earlier about the weather. So when we're bonding acrylic together, that has to be done in a carefully controlled environment, particularly with regards to temperature, as Sam's mentioned and Brian's mentioned earlier, that temperature has a large effect on the size of acrylic. So maintaining temperature during all the fabrication is really very important. So while Reynolds have internal ovens within their factory, none were capable of fabricating the complete size of the pool. So this specially erected outdoor oven, as we call it, was erected in their yard. Within that also, they had carefully fabricated and designed other machines to enable the processing of the acrylic to the quality required. And so here on the rails, you can see another end mill, which is going along and then polishing the edges of the floor panels, which have been joined together, ready for the rail strip, which will be added on. Again, a lot of manual polishing to take out the scoring and the roughness that is that remains after that cutting head. And you can see on the right-hand side is that the vertical wall and then attached to the floor panel. Bonding two materials together, particularly acrylic with a resin, is not a simple process. Largely because we're talking with very heavy panels. So the wall panels about 12, 13 tons. And when that syrup is poured into that gap, the first is, as it goes through an exothermic reaction, it expands, it gives off heat, it creates heat and expands. And as it starts to cure, it starts shrinking again, and it shrinks back past the original nominal joint width. And so if those two panels were kept where they were rigidly, you'd generate tension loads in that syrup. And what you do is you'd form cavitation and bubbles. And obviously bubbles, along with being aesthetically undesired, it can cause stress concentrations in the material too. So Reynolds' expertise in this was really an incredibly interesting, from an engineering point of view. We can see that they have these stillages in which different components can move apart and come back together. And on the left-hand side, you can see the dial gauges, which really show the preciseness of that's required in these joints. And all the cables that are running around in the image, they're all to thermocouples, which are consistently measuring the temperature of the panels. As with any project which we're really trying to break new ground, testing is a very important part of it. So when the pool was fully constructed, and we wanted to carry some load tests, and rather than cap the ends, at this point the stainless steel tubs had been installed on site. We decided to put a bladder in the pool and fill that with water. So we filled it up in increments, and again measured how the pool reacted to that in terms of deflections. And here's Lisa and Isabel. As this was during the COVID, still we have COVID running around the world. Lisa and Isabel had the chance to come over from the Los Angeles office to do that inspection. Again, following that, finally polished on site before being visually inspected. And here you can really start to see that it's got an amazing quality to it, and it's really, really transparent, and you can see a slight ripple through the wall. But to us that was perfectly acceptable, given that we're going to have water sort of sloshing around in this at the end. So on to transport. Well, it was carefully packaged up in this designed cradle and lifted onto a Kenworth truck on its way out of Colorado onto Galveston in Texas. Following shipping and a brief stop in Antwerp, it arrived in Tilford, and I'd really suggest if anybody has a chance to go to a container port, it's a fantastic place. Amazing cranes, and it's things are a completely different scale. Anyway, so it was lifted off, and for its trip to site, it was placed on a barge. So the barge actually docked in Docklands overnight, and at I think it's 4 o'clock on Saturday morning, Brian was there taking pictures of it being loaded onto its very short transport to the site. The following day, it was broken down out of the crate, and last visual checks were made for any damage, because this was the first time it had been seen since it was packaged up in Colorado. So just to make sure that we're happy for the lift to go ahead. As you can see, these are the steel tubs which are already in place on site, and you can see that Bradford, who manufactured it, had a great experience of fabricating stainless steel structures. Here they are, the two tubs either end. We have a crash deck from scaffolding in between, and some scaffolding in between the two buildings to hold all that in place. Underneath the steel tubs, you can see these steel temporary props with temporary jacks in red above that. And just to the right of that temporary jack, you can see the outcrop of a stub column in concrete with the permanent jack. We used a temporary jack, so the construction methodology was using temporary jacks, because that would allow the leveling of those tubs to take place. So as soon as when the loads came on, there could be some further fine adjustments at the end. And you can also see the chap on the left just putting a dial gauge in between that steel stub column and the concrete. So what we wanted to do was certainly make sure that as we put the load from the tension rods into the tubs, we wouldn't have movement. So when the day came, some very careful eyes were kept on the forecast, particularly the wind load. As well, it is lifting 55 tons, and that's a 500-ton Liebherr crane. 750 tons was expected, but due to a problem elsewhere, they couldn't provide that. So there's even more focus on the wind load, but it happened without any delay. And for such a large, cumbersome structure, rig lifted an excellent job lifting it into place with 10 millimeters to spare each side. And this is again, this is the compression stack on the left of Belleville springs, which are conical shaped springs. And this is the hand jack on the orange table in yellow, which is sitting on a stool, which pulls the threaded end to compress the Belleville springs on the opposite building. These were hand operated, so it took the operator a fair old time to put the load sequentially into the two rods, and we were there till gone 1 in the morning. But you can see here now the completed load has been transferred into the into the spring stack. And here, this is just a view across the end of the plant room, so you can see it still. You can see both spring stacks, the small one just underneath the black beam in the distance, and the load is still at this point it's sitting on the temporary jacks. But because it's all been compressed together, it now has its stability system in place. So at the end of the night, the crane could be, the load could be taken off the crane, and that could go on to its next site. After that, in the top left-hand corner, you can see that the permanent jack, but it was ungrouted, and until that was fully grouted, as you can see in the main picture, the load could then be transferred to the permanent jacks, and it would be in its final position as the design intended. And so the first time at this point that we could then start taking the film off, we really started to be able to appreciate the clarity of it. So looking into this, the upstand beam on the end here, that's 15 meters deep of acrylic you're looking in. And you can really see that there is a slight bluish tint, but I mean, it's absolutely superb, and it you know, surpassed our expectations of what we were expecting to see. Again, during commission, what we again were doing was we wanted to verify the completed structure. So we performed staggered fills. So we loaded the water depth by 20 centimeters, and we were monitoring deflections during that period. And you can see towards the left of the image, there's a acrylic block in there, and that's how we measured the water temperature, or the acrylic temperature, I'm sorry. And to take those measurements, we had a total station on each building. So as we know that the two buildings, and as Sam mentioned, the two buildings would move independently. So looking at those two total stations, we can actually subtract or find out what the actual movements are. And we had these telltales, or these reflectors, bonded to the acrylic, which we could take measurements from. At the end of the day, what we did see was this, wonderful play of light from underneath. It really looks as though, at full depth, it still looks as though the water is just a small puddle underneath. I mean, the clarity is really wonderful. And again, next we also have a drain down before the final fill, and final inspection before we hand over to the client. But you can really appreciate the clarity of this now, and it just built on the excitement for, certainly from an engineering point, that it's really coming to life. So a little bit about sustainability now. Sustainability and certainly circularity of material has become ever more important. So while at the beginning of the project some time ago, we were aware that acrylic could be mechanically recycled, that is, it's chipped up and reused. That does degrade the material, so it's really a once only process. However, it was great when on signing the climate agreement, or the climate emergency, we went back to look at those decisions and see what changes had happened. So we went to Mitsubishi, who are the manufacturer for the base polymer that Reynolds used. And what they're now doing is they are taking acrylic and they are reprocessing it. So they call it depolymerization, which is really a jargon for taking the plastic and turning it back into its base material, so which is indistinguishable from a virgin made material, and that there is a sort of slight loss as that's cleaned during that process, but it's really rather marginal. But also it means that creating that sort of new virgin material is also at an energy reduction of 60 to 70% when comparing it to making it from virgin chemicals. And so, yeah, the realization when we hand it over to the client and it's fully filled, it's really rather amazing. I mean, I think that it's set out to do exactly what the client's brief was. It's as though you've got a big pool of water sitting in between two buildings, really nothing holding it there. And it's really, you always want to be able to, look back at the renderings and see how it performed. But in this case, it's, surpassed that in many ways. So we're all very pleased with the results. I'm sure you've seen those a lot in the press recently and in various places. So now I'd like to hand back to Lee, who will be able to round it all up and provide his thoughts.
Hi everybody, some amazing images there. A huge amount of effort taken to refine an amazing concept. We've got lots of technical questions flooding in. I'm going to quickly summarize groups of them and ask the Eckersley O'Callaghan team to pick which ones they want to answer. Jonathan Louth asks, does acrylic discolor? Or like Perspex, does it remain quite clear? And I think he mentions the replacement philosophy for that indefinable point in the future. And perhaps somebody could answer that one for him. Alexei Fokin, this one is a bit beyond me, Alexei. How did you tackle the LTB of the deep plastic beam with no restraints of its top flange? I think that's definitely an engineer's question.
That's lateral torsional buckling, Lee.
Thank you so much, Brian.
Sam will explain what it is and how it was dealt with.
Well, let's just start off with those two first of all. Does acrylic discolor and LTB?
Yeah, I can take those if you like. So yeah, does acrylic discolor like a Perspex, or does it remain clear? So first thing to state is that Perspex is actually acrylic. It's a brand name for acrylic, just like Hoover is a vacuum cleaner. So Perspex and acrylic are the same thing. So you will have seen discolored Perspex acrylic, but the guys at Reynolds have a secret formula they have UV stabilizers or absorbers in their acrylic, and what that means is that you don't get UV light penetrating deep inside the acrylic, and any degradation happens right on the surface. And so as part of the regular maintenance regime, they will come and polish out any kind of crazing that might occur, or any kind of discoloration or anything like that. I'm sure the guys at Reynolds could explain it better than me.
And what about,
that's my understanding.
And what about the replacement question? Is that one for you, Graham?
Well, yeah, it has been designed for a 20-year life, so that that comes along with the annual maintenance and careful maintenance of the project. So we see that it's there for a considerable time. And as I mentioned briefly, if we were to come and replace it, we can then recirculate the material back into effectively the same structure. It's
and what about that more technical question about tackling the LTB of the deep plastic beam?
Yep. So as Brian said, LTB is short for lateral torsional buckling. So you get this happening with beams, steel beams, for example, you always need to check for lateral torsional buckling, and it's basically it's a type of failure, but instead of the material breaking, it's when it kind of, to put it in layman's terms, kind of when you load it and it kind of twists and flips and kind of flops out of position. So it's a failure, but it's not a material failure. And basically, to answer specifically on the sky pool, you kind of get a sort of U-frame effect, so that the bottom of the pool kind of supports the sides of the pool. So if the sides were there by themselves, they'd be a lot more prone to kind of flopping out of position, but you've got this nice kind of rigid structure at the bottom. And then also, if you go back to what I was saying before, we're designing this to 5.5 megapascals, which is a very, very low stress, which means that actually the forces on the sides are actually comparatively low. So if you were to really kind of stress it and add loads more load, then there would come a point where it would buckle. But at the very low stresses, we don't see that happening.
What about the Jacques Anso asks, what are the anticipated long-term effects the structure would experience from chemicals used to maintain the pool? And just to say, I think we need to keep some of the answers fairly short so we can...
I can answer that one again. I mean, the acrylic material has been used for pools for a long time. So it's really about conditioning of the water as being use particular chemicals and how it's cleaned to make sure that they're compatible with the acrylic, and that's not
okay. And Sam Gregg, Will Wild asks, is crazing only induced under tensile, or does it also occur under compressive stresses? Is that one for you, Sam?
Yeah, I can take that. Crazing is a tensile stress because it's cracks, so it's opening up of the surface. It doesn't really happen under compressive loads.
What happens if you get too much compression, though?
It will fail, but it won't craze. It will fail in a different way. And
does the thermal... Simon Burrell asks, are there any fatigue considerations with the expansion and shrinkage of the material?
So again, like we consulted with Reynolds Polymer, and they've been designing to this 5.5 megapascal, and that's what they use, and based on their years of experience, that's sufficient for these kinds of structures. Oh, have
we've lost you, Lee?
Lost Lee.
Should we ask some of our own questions, or read some of our own questions whilst we wait for Lee to come back? Was there any pre-camber to the acrylic? The answer is no, there wasn't any, because the deflections were such that wasn't necessary over the span. Material used for the tension rods. I think a couple of people have asked that. Sam, do you want to talk about that?
Yeah, that was a high strength stainless steel.
And
from Tri-Pyramid, I believe. I think it was.
Yeah, and related to that, the turnbuckle joints of the tension rods in the middle of the span. Why were they in the middle of the span where no one could adjust them?
Well,
don't have.
I mean, the turnbuckles there aren't really for adjustment. They're there because the rods can be manufactured in the length, in the 17 meter or so length that's required. So it's a fabrication.
So it's actually the joining piece between the two halves.
That's it.
Adjustment is done in those jacks, which, if you were paying attention, Alfred, you would have seen Greg carefully explaining how they were tightened up. Lee, you're back. You can carry on.
I'm not sure that I can actually. Something seems to be interfering with my internet connection. I think, Brian, it's safest if you carry on at this moment.
Oh, we can
till I
hear,
get on more.
we can hear and see you clearly right now.
Yeah, can you? I can't see all of you, I'm afraid, and I can't see the questions. So,
Oh,
Brian, I
okay.
think.
Okay. Let's see, what else have we got here?
There's one from Adrian Betanzos. Is there a limit to how many times you can polish the material? Really, the polishing really removes very small amounts of material. As Sam mentioned previously, the crazing are really microns thick, so typically 0.1 to 0.25 microns. So what you're doing when you're polishing material, you're locally heating up till it starts flowing on a very microscopic level, and then it redistributes itself. So it's not the same as sanding and removing material.
Although, well, there has been a kind of an inch or a few mil kind of added on to the thickness to allow for any polishing or kind of removing of material. So there is that allowance there.
Someone else asked a question about seismic loading. Well, in London, there isn't any seismic loading, so that wasn't a significant design load at all here. But then someone else has also asked, is this approaching the limit of what is achievable, and could the same be realized in a seismically active country or a country experiencing typhoon winds such as Taiwan? Well, the answer to that is yes. The structural thicknesses and depths may need to change to deal with some of those greater loads, and maybe some other special features may need to be built in order to deal with seismic activity, for instance. But in principle, yes, there's no reason why a similar thing couldn't be achieved in those conditions. Mark Lee, hello Mark. What a feat of design and engineering. Have any of you had a swim in the sky pool yet? Sadly, most of us haven't. I think only Hal has. Is that right, Hal?
You may be right, Brian. Yeah, I have swum in it, obviously for testing purposes, but and I'm terrified of heights, but it's interestingly, you get a sort of full sense of security, maybe, in terms of being enveloped by water. So actually stepping off the edge, while extraordinarily dramatic, it doesn't feel as scary as I thought it might.
Thanks, Al. And we're hoping for the invite from Eco World Ballymore any day now to be able to get our swim as well, which we've been looking forward to for approximately 7 years, I think. What else do we have? How have you dealt with water tightness between the steel tubs and acrylic, given the differential movement, vertical and horizontal rotation, and different thermal expansion from Wolfgang? Hi, Wolfgang. Sam or Graham, which one of you wants to take that?
Yeah, so the whole thing is all tied together, so it kind of moves as one piece, separate to the movement of the buildings. So there's not really any movement in the joint, and as explained earlier, the tensions help to kind of keep this all together as one unit.
And Duncan Walters, our very own Duncan Walters. In fact, what adhesives do you use, Graham? Maybe you could take that.
Well, if Duncan's referring to the adhesive to bond the panels together, it's an acrylic syrup, so it's almost identical to the apparent material, and it forms a chemical bond between them. So it's not so much an adhesive; it's actually a chemical bond. But in other aspects, we've got silicone, which bonds very nicely to acrylic as well.
And there's a bit of cementitious grout in there as well, to where the acrylic pool sits on the steel. Bit of grout there too.
Okay. Alexei, thanks for asking the LTB question. Another one, please. Is there any long-term degradation of the physical and mechanical characteristics of the exposed plastic subjected to sun radiation together with temperature variation? I think we've sort of addressed that, but Sam, do you want to say anything else on that?
Yeah, it's to do with the Reynolds secret formula, as I explained, with the kind of UV absorbers. But I'd also add that we did do some testing on the acrylic. So we did some accelerated aging. We did tensile tests on little samples and made sure that we were happy with the strengths there. So that's how we ensured that wasn't going to be an issue.
Okay. And has our experience in this project led to any consideration of using acrylic in place of glass for some of our other projects? Yes, it has led to those considerations. I mean, this sort of transparent bonding that you get, which means that you can, join structural components together in a completely transparent way, makes it a really exciting material to use as a solution in particular places. But it certainly is not a replacement to glass in all situations. For some of the reasons that we said earlier, it's much weaker, it's much less stiff, so the components end up being much bigger to carry the same amount of load. So it doesn't have that sort of fineness of a structural material that you get from glass in that respect. Also, you can scratch it, and just walking on it in shoes would scratch it, for instance. So it's not the ideal material to use where people and objects are coming into contact with it, where it could be damaged. So again, that's an important consideration. But certainly there are some situations where it's the perfect material to use, and this was certainly one of them.
I think another thing is the kind of coatings that you put on glass. If you're using it in buildings and you want to keep the thermal energy, solar radiation out, the coatings that you can get on glass are really kind of high tech and really help with the performance of the buildings. So that's another kind of benefit for glass. But the real strength of acrylic is this seamless bonding. So any kind of huge kind of structures, then acrylic might be the way to
go. Fire performance of the material. Graham, do you want to address that?
Yeah, sure. I mean, obviously that's something that is very important in the design of any structure. So what we chose to hear with Hawley, who are the fire engineers, we looked at how we could protect the acrylic, and to that extent, and there's extra precautions taken for the apartments around and underneath the sky pool. So we're mitigating those facts by preventing hot gases and flame escaping out, which could cause any flame onto the acrylic.
Thanks, Graham. Every time I think we're finished, another one pops up. So did we take into consideration the added vertical load by the pool in a part of the existing building can change its behavior at different periods? Yes, that changing loading was absolutely considered in terms of its effect on the existing buildings. We were not the engineers. Well, they weren't existing buildings anyway. They were new buildings which were designed to take this loading. We were not the engineers for those buildings, but those engineers did fully take into account those loads. How about any other materials for the tendons? Is there any? And how about their visibility? What does the client think about it? And you, I presumably you mean what does the client think about the tendons? Yeah, I mean, it would have been nice if they weren't there, but they were a very important aspect they had to carry a high tensile load and be robust and minimal and exposed to the weather. So high strength stainless steel did seem like the appropriate material to use to get the most minimal result with the appropriate longevity. It would have been nice if they weren't there, but they're not very obtrusive. When you see it in real life, they're not very obtrusive, and they perform an essential function in ensuring the robustness of the structure, in holding everything together to keep it watertight, in, as Sam said, in making sure everything moves together. So I think the client is absolutely fine that they recognise what they're doing.
I'll just add to that, Brian. I was down there earlier today, actually, and looking up, and suddenly looking back, and I realised I didn't even notice them.
Yeah, I mean,
your eye is drawn to the activity in the water. You just sort of, that's where your eye goes, and they sort of fall away, as it were.
Yeah, I mean, we all tried to engineer and design a solution that didn't need them, but yeah, they had to be there, and then they're really not that obtrusive, I think, in the overall scale of the structure.
In terms of other materials, we'll wait a few years and then we'll have a transparent aluminium, right? When that becomes a bit more affordable, we'll
high tensile glass maybe in a few years' time. Pool eliminated below the waterline from the adjacent buildings. Yes, it is. That was an easy answer. So I think that's pretty much all of them. So I'll say thank you to everyone that's joined us. I think we've had the biggest audience by far of any of the webinars that Eckersley O'Callaghan have been running over the past few months of the pandemic. We had over 1,000 people on this one, and filled up the number of available slots that we had. So thanks to all you guys for taking part. A special thank you to EcoWorld Ballymore, who are our clients on this project. It has been an amazing project to work on. Quite clearly from the beginning, it had this fantastic ambition and of creating the most transparent possible structure spanning between these buildings. And it's been a very difficult journey in many ways. Perhaps we made it look easy, but we've avoided maybe a lot of the headaches along the way, the problems that had to be solved. And Reynolds Polymer were the guys responsible for solving many of those problems. This was something that they were fabricating that was far bigger in scale than anything they had done before, and far more complex. And as Graham explained, that required building a special oven, a temporary oven outside of their factory in the freezing cold temperatures of Colorado that could heat and anneal this structure in a super controlled and sensitive way, and that was a real headache. And they solved that problem and delivered the structure at the end of the day. And meanwhile, EcoWorld Ballymore never wavered in their support and commitment to this as a project. Many clients would have gone off the idea much sooner, and they stuck with it. And I think the result is a sort of testament to their patronage. And it is a private pool. Most of us haven't swum in it. People in the sort of social housing blocks that are part of the overall development, there's been some controversy about the fact that they don't have access to it, and that, of course, it is a great shame. But it's it's part of the nature of the whole development, and that the service charges, the housing associations weren't keen on supporting those service charges for this part of the project. but the thing is, I think, you know, we haven't swum in it, but I don't think you have to swim in it to appreciate what a wonderful thing this is. You know, I was down there at the weekend, and there are lots of people wandering around, taking pictures, commenting on it, smiling about it. It is a pretty beautiful thing. The way the light passes through it is a beautiful thing. So you know, I think we can all enjoy it from that point of view. Anyway, thanks everybody. Thanks for joining us, and see you soon on our next EOC webinar.